This is the 6th lecture, the part 1, part A, let's call it part A. Today's topic is the Cauchy Residue Theorem. Cauchy Residue Theorem. And we begin with the typical setting and consider an analytic function so write it down, f from U to C. So U is a domain in C, and an annulus, put it like this, A is equal to the set of all Z, such that this is inner radius of this annulus, and there is also the outer radius R2, so R1 smaller than R2, so this is an annulus, such that A is contained in the domain of U. So that, let's say, requires some kind of a picture. So suppose this one is like this is my U, and then we have this annulus, which is something like this. And Z0 is here, this is Z0. So we have here the two radiuses. So this is inner radius and this one is upper radius. So this will be R2 and that one is R1. And this is of course your A. So now, what are we interested? We are interested in a part. So suppose here we have a contour. The contour is in the annulus, so put it clearly, assume that C contained in A, so this is my C, this one is of course A, is a simple closed contour surrounding, so going around the point Z0. That means simply that Z0 belongs to the interior of the region bounded by C. So now our question is this one. So let's put it as a problem. Compute, and we want to compute an integral. So this is integral over C of this function f of z dz. So now, remember, so by Laurent expansion theorem, the function f of z has a Laurent series expansion. At A means centered at Z0. So let me write this expansion. So this will be like f of z can be written, and this is big sum, n is equal minus infinity, infinity, and this will be a n z minus z0 to the power n, and here z belongs to this annulus. So in particular, we have, and we can write it down, integral over cf of z dz is equal, and here we have integral c, and we can substitute for the function the series. Now it is a Lorentz series. an z minus z0 to the power n, that will be dz, and then there is this property. We can interchange these two symbols. And by interchanging, that means simply we can rewrite it, we can write it down. Sum goes first, minus infinity, infinity, an goes here, and here we have contour, and this one is z minus z0 to the power n dz. And here I have a very nice thing. If this n is different than minus 1, the function, this function, has an antiderivative. This is z minus z0 n plus 1 divided by n plus 1. And that means we can use this fundamental theorem for complex integral. And that means, since this is a closed contour, so this integral will be equal to the value at the end minus value at the beginning. These two values are the same, so the integral will be 0 for all those numbers. So this integral will be 0 for n different than minus 1. So the infinite sum disappears, and now we have only the term minus 1, and this is c, and I put here like this, 1 divided by z minus z0 dz. But that integral, look, just use the Cauchy integral formula for the computation. We know that function f of z is 1, so you are getting immediately, this is 2 pi I, and this is a minus 1. So as you see, there is a special, this coefficient a minus 1 has a special role, special role. This coefficient allows us to compute such integrals. So let's go and concentrate on an isolated singular point. Suppose now that z0 is an isolated singular point of the function f of z. So then of course we have this point, let me put it like this, this is my z0, so there is this isolating neighborhood, and as you see this is also like annulus, so I have here the Lorentz series expansion, so f of z can be also written as the Lorentz series expansion, n is equal minus infinity, infinity, and this will be like a n z minus z0 to the power n. And of course we have immediately, so this is small contour here, so this integral of c f of z dz is equal 2 pi I, and again put it again a minus 1. So this will be a minus 1 coefficient, so that minus first coefficient of the Lorentz series. This is a Lorentz series at z0. So therefore, look, this is important element and important information about the function. It allows us to compute this integral we give a name to it. So put it like this: definition and notation. And notation. A minus 1, this coefficient A minus 1 is called the residue of f of z at the point z0. And the notation will write simply, instead of writing a minus 1, we will just write like this: res standing for a residue. This will be f of z, and this will be z0, because that's a singular point z0. Singular point z0. And now we can formulate our main result, and the main result will be theorem. That's one of the principal main results of this course. And we simply write it down: Cauchy Residue Theorem. And we say like this, okay, let, the same as it was before, let U be a domain F from U, why cannot make a nice two dots, U to C, an analytic function and C contained in U a contour. So put it clearly: simple, connected, closed, simple closed contour, positively oriented, of course, such that the inside of C, which is a domain, such that the inside of C, inside means, maybe I should explain, such that in the area bounded by C, there are only finitely many singular points, and let's say of Fz, say those points, they are, say, we have here, say this will be point Z1, Z2, and Zn, finitely many. And there are no others. So 10, we have, and we can write it down, the integral over C, f of z, dz will be equal, again, 2 pi I, and then you have here the sum, k is equal to 1 to m. Those are the counts of the singular points, and this will be residue of the function f of z at the point zk. Maybe we need a we need also to illustrate the situation on the proper picture, so let's begin the proof and let's illustrate it. Proof, and here we have the following situation. So what do I have? This is my contour. I just ignore U. This is my contour C, and now I have singular points inside. There are no other singular points. Remember, there are no any islands like this. Oh, you see, the island is not domain. This is not possible. If you remove this set from the domain, the function is not defined on the set. They all are singular points. It is not possible. So there are no little islands like that. So that means there are only points which are z1, z2, z3, blah, 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 and then of course zn is the last one. So that's the situation, and that means in our case, let me make a little picture. So I notice, since the points there are finitely many of them, they are definitely isolated singular points. So those are isolated, zk is isolated. So I can find a small circle around each of them, and this circle do not intersect. So those denote, this one will be circle C1, this will be C2, this will be C3, and this will be Cn, the last one. They are all oriented positively. So we have here n circles. And now you can look at the area which is in between these circles and the contour C. So which area? This area. Look, this area. Now I'm shading the area in between these two circles. So call this like greenish or yellowish area just simply G. So I call this one G. So this is in between these circles. So put it like that. We choose small isolating neighborhoods of the points zk, and inside these neighborhoods small circles ck. Then the region bounded by the interior, maybe I should give the name to this region, the region G. So this means this region bounded by the interior of C and the exteriors of CK has boundary gamma. So let's write it down such that, let's look at this one. So the boundary of G is the contour gamma, and this contour, and you can see it here, this is the C, that's the one portion. So this is contour C. But then you go here, but when you want to have the boundary orientation as the boundary, so there is the rule, so this orientation will go other way. So that means we have to write it now. It will be not C1, C2, it will be minus C1, minus C2, and this will be minus Cm. And then, once we are here, so we can say like this, the function f of z is analytic in G closure, on G closure, maybe make it on G closure, thus, why it is not written nicely, G closure, thus, we have here by Cauchy theorem, we have here that integral over gamma f of z dz must be equal to 0. must be equal to 0. But this integral, so let's rewrite it. So, because this is the boundary of a region where the function is analytic, so Bursa gives you 0. So, but that boundary, you can rewrite it. This is the same as boundary of C, f of z dz, and then you have here minus, and this will be sum, and this will be k is equal 1 to n, and this will be integral over ck f of z dz, and this one is equal 0. And then clearly, what do I have here? I have here that this integral z dz is equal, actually, this sum of integral, this is 1 to m, did I do it correctly? M, yes, m, correct, m everywhere, and this will be integral ck f z dz is equal to z, what I'm writing? Okay, is equal to, and look, we just computed this integral above in the previous page, so let me go there. So let me show you, we just computed it. This integral is equal, so that's equal, let me point it out, will be 2 pi I, and this r minus 1 is called the residue of f of z at the point a z0. So in our case, we also have the same situation. You can write it now. This is equal to 2 pi I, and that one will be residue, and this will be f of z, and in this case is zk. And of course, that's the formula we were proving, so the issue is closed. So the theorem is proved. So as you notice, the computations of these integrals, so is reduced to the computations of the residues. So remark, computations of the integral, and this is cf z dz, was reduced to the, let's put it like this, reduced to, and we put it in for, so pay first a the identification of isolated, of, let's say, of, maybe you should write singular points, all of them, singular points inside the curve, the contour C. And the second one is finding the type of isolated singular point, and C, computing the residue at that point. So let's start. We have three types of the singularities. So 3 types of isolated singular points. Maybe I should put my glove, because you see it's better to write with the glove, so you don't touch screen with the hand. 3 types. So let's start with the type 1. So this is first type, and this one is removable singularity. So if this is Z0, if this is removable singularity, then clearly residue in this point f of z at that point, so it's 0 because the Lorentz series put it like this, then you have the Lorentz series which is composed only of the analytic part. Principal part is non-existing, so principal part is looking like this. This is P of z, we call this principal part, is n is equal to 1 to infinity, and this one is a minus n, and the powers are z minus z0 to the power is just 0. That means all these coefficients are equal to 0, so a minus 1 is also equal to 0. Why it makes this? So all these coefficients are equal to 0. A minus 1 is also equal to 0. So there is nothing to compute. So the second type is the pole. So let's start with the pole. There are actually, this is actually kind of interesting. So pole of order, and let me call this order m, don't get mixed up with the theorem that we were proving before. So if this is pole of order m, so this is again z0, so this is at the point z0, so we have here that in our case the function f of z0 will have negative powers in the Lorentz series expansion, starting with the a, and this will be minus m, and here we have here z minus z0 to the power m. So that value here, that value m, a minus 1 is the first value which is non-zero, and after that there are no other negative powers, so this is called the order of the pole, as you remember. Then you have here a minus m plus 1 divided by z minus z0 m minus 1, and then we go and the residue is here. This is our residue, a minus 1. That's the guy we are hunting for. So we have many coefficients, but for us important is that one, z0, and then you have here a0, then you have here a1, z minus z0, and then plus, and then maybe a2, z minus z0 square, and okay, other powers. So we are trying to compute that guy. So what can I do? I'm thinking about like that, how to get that coefficient. So I see that in this case, if I multiply the function f by z minus z0 to the power n, and I put here f of z0, I will get this particular, not a Lorentz series, but it will be already a Taylor series. So this is a power series of a certain function. M, not m, this is just simply 1 plus, okay, let's wait, okay, to the power 1, and then you have here plus, and then you have here a, okay, this should be red, of course, because this is the one that we need, and we have here the, let's say the power, this is a minus 1, and the power here is z minus z0 m minus 1. So this is the power is plus, and then you have here a0 times z minus z0 to the power m plus other. So we want that one, we want that one, we want that one. But look, this looks like a regular power series. So let me recall, if you have a power series, I changed the color to make it sure that this is going to be different, seen differently. If you make a little margin here, if you have here a power series, so call this function like a g of z is my power series, and here we have here A, call it B0 coefficient plus B1 Z minus Z0 plus, and this will be Bn Z minus Z0 to the power n plus others. So we know how to compute this coefficient, because Bn in our case will be just nothing else, and accordingly to the fact that we know that power series represents in definitely an analytic functions, we will need to take the nth derivative of g at the point z0 and divide it by n factorial. Here, however, if you would like to do the same thing regarding the function f, we may have a problem. So here we may have a problem. The fact that we have, and in this case it will be removable singularity, at z0 of the function, which is this one. This our function is gz, in this case is z minus z0 m, and this will be f of z0. That does not allow us effectively compute derivative at this any, put it like this, an m minus 1, which will be our n, at the z0, because the function is not defined, may not be defined, because g at z0 may not be defined. It can only be, you see, it has a power series, it can be extended, but we don't know what these values are. So that means you cannot also compute the derivatives directly. But this can be overcome. So namely, in such a case, let's formulate this as our results, theorem. After this introduction, we can write it down. If f of z has at z0 a pole of order m, then we have. So remember, which coefficient we are looking at? We are looking at this coefficient. Let me change it. This is m minus 1. So your n, in our case, is m minus 1. So here will be the following formula. From this formula, we can write it down, that residue at f of z at the point z0 will be equal 1 divided by m minus 1 factorial. And now we can compute the derivatives at the points close to z0, but in this case it will be limit, and this will be z goes to the z0, and then you have here the derivative of the gz, which will be dzm minus 1. This is m minus 1. Okay, I try to rewrite it in such a way it should fit. Let's see, I start here. The residue of f of z at z0 is equal 1 over m minus 1 factorial. This will be limit as z approaches z0, and then we have derivative, and this is m minus 1, and this is dz m minus 1, and here we take the z minus z0 to the power m, f of z, and that's the formula. That's exactly. Just remember, like it was previously said, that was our, sorry. I need to change the color. This was our g of z. This was our g of z, so that will be the coefficient. So where is our g of z? Here. That's the g of z. This is just g of z. And then that's why we have this formula. So let me point out that the formula will not be effective for m large. That means if n is equal to 3 or 4, sometimes it will be very difficult to compute this residue using this formula, and especially when you will have involvement of trigonometric functions. So put it like this: for m, the formula may not be effective. Why? Because in the case of complex functions, the computations of the limits can be complicated. You know it already, that limits of complex expressions, even in the case of the real functions, can be kind of difficult. So here is, okay, additional problems. Yes, it can be even more difficult here also. But in certain ways they're almost the same. It's almost the same situation. So let me see the situation which is relatively simple. The case of a simple pole. Simple pole means m is equal to 1, and this is really easy one. So in this case you can see that the residue, let me write it down again. So this will be in red. So the residue in such a case of f of z at a simple pole looks like this. So what is this? This is just simply equal to limit as z goes to z0, and then you take z minus z0 divided by f of z. That's the formula. This is the formula here from above. So this is formula star, written for m minus 1, so call it 2 stars. But also, if you have here, for example, the situation when your function simple pole, so let's say the case when f of z is equal, put it like this, p of z and q of z. So here we have the simple pole, so that means p of z0 is equal to 0. And you should remember it from the previous lecture. So that one is equal to this, this one is different than 0, this one is equal to 0. But simple pole will mean that that one is not equal to 0. So in such a case, we can definitely apply this formula, and let's see like this how it would work. So in this case, we have here the residue of f of z, and I put it like this at z0. This is simple pole, remember, so it will be equal limit as z goes to z0. So I use the expression here, so put it like this. This is z minus z0, and then I have here p of z, and this is divided by q of z. So let me continue here. So this will be the same as a limit. This is z minus z0. I put here z minus z0 divided by q of z. But since q of z0 is equal to 0, so maybe let me point it out with red. Look here, this one is here, so I can plug it here. So I put here minus q of z0. 0, so I'm not changing anything. and times limit as z goes to z0, and this is, sorry, p of z. So you watch it and you see, well, what is this expression here? This expression is not interesting. Write it down differently, maybe a little more different, even like this. 1 divided by limit, and this will be q of z minus q of z0, and this is z, and this is z divided by 0. So this is limit of this ratio. So this is the, have I seen this before? Yeah. So that one will be p of z0. But what is this one equal to? What is this one? So you look, that looks like a definition of the complex derivative. So yeah, this is a complex derivative, so you are getting here pz0 divided by q prime z0. So put here like this, theorem. And we have here for find f of z equals p of z divided by q of z with this condition. So this is simple pole, z0 simple pole. That means p of z0 different than 0. Q of z0 is equal to 0, but q prime of z0 is not equal to 0. We obtain that residue of this p of z, q of z at the point z0 is equal p of z0 divided by q prime of z0. And then there is a kind of a similarity with something like you have already seen. So let me do a problem. So that would be like this example, and this is example from the past. So I will do it like this. Suppose we have, okay, maybe just simply write it down. Compute the following integral. Example. Compute the following integral. And let's do it. I will do it like this. So I put it like this. So this will be like a, take a c, and now I put here, okay, let's put it e to the z divided by z to the power n. Let's say plus 1 dz, and then we have to understand that the equation, so I make a margin here, this equation zn plus 1 is equal to 0, so can be solved using there are n roots, so how many roots are there? So this is the same as zn is equal minus 1. So you take the unit circle, and then in the unit circle you look for the first root. So this is your root z0, which is equal e to the I, and this is pi divided by n. So then of course you have another root z1, another root z2, etc., another z3. So let's assume that the circle, the contour C is a small circle around the z0 root. So I add it, so put it like this, where the contour C is a small isolating, not nice to write it, isolating C is a small isolating circle around the root z0. So that's definitely singular point E, and this is I pi divided by n. So that's the circle C. So okay, let's compute it. So notice that z0 is a simple pole of f of z, of f of z equals e z, and this one is z to the power n plus 1, which is exactly pz divided by q of z. So you have here e to the any number z is never equal to 0, but q of z0 is equal to 0, but q prime of z0 is equal to n. Zn minus 1, 0 is not equal to 0, because we have it computed. So now I can basically write the answer. Therefore, I can write it down that integral over this circle Ez, and I put here z to the power n plus 1 dz is equal to pi I, and then I have here e to the z0, and this one is n, and I put here z0 to the power n minus 1. And this can be simplified, and by the way, here, this expression, it reminds you something that we were already doing in the case of the Cauchy integral formula. And I remember I derived such a formula, I don't know, probably from -1. It was kind of a similar situation, but now you can see that this is n z0 n minus 1. Let me do similar things as we did before. So then I'm getting here that this integral is 2 pi I. This becomes -1. So I can put here minus, and this is n. So n goes here, and then you have here e z0 times, and here you have here z0. As I said always, that answer in the symbolic way is not acceptable. It has to be always in the standard form. So let me write it down. Z0 is equal, and you should remember what it is. This one is equal cosine pi over n plus I sine pi over n. So let me rewrite this answer. So this is minus 2 pi I divided by n, and then you have here like this. Maybe this is e to the power cosine pi n, and here we have here cosine of sine pi n plus I sine of sine pi n times, clearly I have no space, times, and I write it down, cosine pi n plus I sine pi n. I have to do something about it. Okay, let me finalize. So let me, this what me write it down. This was minus 2 pi I divided by n. I copy it again. So again, I'm making the same, e to the power cosine pi over n, and this will be cosine sine pi over n plus I, and this will be sine pi over sine pi over n times, and here we are getting cosine pi over n plus I sine pi over n, and we are getting the answer. The answer will be first, this is minus I times I, it means the imaginary part will change to the, so put it like this, 2 pi n, and then I have here the real part will be this times that and this times that, so this will be cosine sine pi over n times sine pi over n plus sine pi over n, and this will be cosine pi over n, and that's the real part, plus I, and the imaginary part will be actually, let me do it one more time, this will be minus, not plus, because I have here minus, so this will be minus again. Maybe just close it, and the imaginary will be just simply I, and put it like this, 2 pi over n, and here I have here, and here I have here cosine sine pi over n times cosine pi over n minus sine pi over n, and this will be sine pi over n, close it. So this will be imaginary part of this. That's the acceptable answer. So remember, your answer always attempt to write in the proper standard form, because remember, complex number represents a vector. If you're talking about a vector, you should be able to get a formula expressing its coordinates. Real part is the first coordinate, x coordinate, and the imaginary part is y coordinate of this vector. So it is always possible to effectively plot this vector, to have an information about its properties. So this is basically the end of this lecture, except we have one more case. Maybe I should cover it before we go. So this is the last part. This is essential singularity. And since this is essential singularity, so in this case there are no any formulas to learn, so it's a good news. But the bad news is that basically in this, for the computations of the residue you need here. So basically we need to be able, we need to compute, maybe let's say, we need to compute the Lorentz series of f of z. So quick example. In this case, it will be the function f of z, just for simplicity, the one that we considered in the previous lecture. So we know that this has a power series starting, so this will be like a number 1, so this will be 1 divided by z, and this will be minus, and this is 3 factorial divided by z to the power 3 plus, and this will be 1 divided by 5 factorial z to the power 5 minus. So you can clearly identify that this is the power a minus, so this is coefficient corresponding to the residue, a minus 1. So this is the residue. Z0 equals to 0 is essential singularity. But we know what is the Lorentz series expansion, so we can write it now. Residue of f of z at this 0 is equal to 1. Similarly, if you need another example, of course, if you know what is the residue, what is the power series expansion of the exponential, of course you can write it down again. This will be 1 plus 1 over z plus 1 over 2 factorial z squared plus 1 over 3 factorial, that's so ugly, 1 over 3 factorial z cubed, and plus again. You recognize, wow, this is my coefficient a minus 1, so that means you are recognizing residue of this function 1 over z f0 is again equals to 1. And I am planning to do several other examples and also to show you additional techniques for the computations of the residues. Some of those residues, especially when we are dealing with poles of the multiplicity, that means of the order larger than 1. So in the case of the m equals 2, generally it is possible to do the effectively differentiation and computations of the limits. However, it may be difficult if you are dealing with trigonometric functions, which usually lead to kind of a weird limits. So I will show you the other alternative methods that allows you to compute these residues effectively by doing some kind of a shortcut to power series expansions. But this is going to be in the next part. So for now I'm saying, for me it's a good night. So bye bye.